Okay, let's dive right into this explainer. We are going to completely challenge everything classical physics ever taught us about the nature of reality. For centuries, scientists thought they basically had the universe figured out, right? Light was this continuous wave rippling through space, and matter was made up of solid, predictable little particles. It was a very neat, orderly Newtonian world. But as we're about to see, the universe had a massive, mind-bending plot twist waiting for us right at the turn of the 20th century. To really grasp the quantum realm, we first have to stop and ask ourselves a question that flipped our entire understanding of the cosmos upside down. What if light isn't just a wave? And what if matter isn't just made of particles? Actually, what if that strict dividing line between the two just straight up doesn't exist? The unraveling of all that classical physics started with one very specific, super puzzling mystery called the photoelectric effect. Now, the contrast here is wild because classical physics completely failed to explain the photoelectric effect. Here's the setup. You shine a beam of light onto a clean metal target, and that light ejects electrons right off the surface. Now, classically, since they thought light was an oscillating electromagnetic wave, shining a brighter, more intense light should have given those electrons a much bigger, more energetic kick. But guess what? That is absolutely not what happens. Cranking up the brightness didn't change the maximum kinetic energy of those ejected electrons at all. A blindingly bright light and a super dim light gave the exact same energy kick. The only thing that actually changed the electron's energy was the light's frequency. Enter Albert Einstein with our first major plot twist. In 1905, he proposed that light actually isn't a continuous spreading wave. Instead, it's quantized. It is made of elementary, truly discrete little packets of energy called photons. Imagine light not as a steady stream of water from a garden hose, but more like a rapid-fire barrage of individual, energetic hailstones. When light interacts with matter, it transfers energy in these single, indivisible chunks. And this brings us to what is basically the source code of our universe, Planck's constant. We represent it with a letter H, and it is exactly 6.63 times 10 to the power of -34 joule seconds. I know, a number that incredibly small is hard to even wrap your head around, but it's the fundamental scaling factor of all quantum mechanics. It dictates the exact sizes of these energy packets and governs literally all quantum interactions. You physically cannot have an energy transfer smaller than what this constant allows. So, looking at this crucial formula, E equals hf, a photon's energy is directly tied to its frequency. Energy equals Planck's constant times frequency. And boom, this elegantly solves that whole photoelectric puzzle. Increasing the intensity of the light just increases the sheer number of photons hitting the metal, not their individual energy. But if you increase the frequency of the light, you increase the energy of each individual photon. By the way, this exact principle is literally what makes modern tech like solar panels and digital camera sensors actually work. There is a catch, though, for those electrons trying to break free. They're held inside the metal by electric forces, and an electron only escapes that surface if the incoming photon's energy is higher than a specific barrier called the work function, which we show as the Greek letter phi. Think of it like a strict entry fee at an amusement park. If a single photon doesn't have enough energy to pay that exact fee all in one go, the electron stays trapped, no matter how intensely you shine that light on it. It absolutely needs a specific threshold of energy in a single hit. But wait, this leads us to a massive contradiction, doesn't it? If we're treating light like little projectile packets hitting electrons, we have to talk about momentum. Now, classically, momentum is just mass times velocity, but photons are light. They have absolutely zero mass. So how in the world do they physically knock electrons around? How can something without any mass at all possess physical momentum? Well, Arthur Compton actually solved this mystery in 1923 with a brilliant scattering experiment. He fired X-rays at a carbon target and found something unbelievable. The X-ray photon literally acts like a billiard ball. It smacks into a loosely bound electron and transfers momentum right to it. The electron recoils, gaining kinetic energy, and the photon scatters away. But because that photon lost energy in the crash, it leaves with a lower frequency and therefore a longer wavelength than it came in with. We call this the Compton shift, and it proved once and for all that a totally massless photon acts exactly like a physical particle. So light, this thing we were so sure was a wave, behaves like a particle. Well, if light can pull off a trick like that, French physicist Louis de Broglie asked the ultimate rhetorical question in 1924, launching our second massive plot twist. He appealed to the fundamental symmetry of the universe. He basically said, look, if waves can act like particles, why on earth can't particles, like the electrons that literally make up our bodies, act like waves? De Broglie hypothesized that all physical matter actually possesses a wavelength. He took that momentum equation for a photon and just flipped it, giving us this beautifully simple relation: wavelength equals Planck's constant divided by momentum. This means any moving particle, like an electron, is described by a matter wave. Now, because Planck's constant is so incomprehensibly small, we obviously don't notice the wave nature of big things like baseballs or cars. But for a tiny, fast-moving electron, that wavelength is a huge deal. Just look at these experimental results. It's a double-slit experiment using actual physical electrons. When they're fired one by one, they strike the screen in highly localized little dots, exactly like solid particles should. But wait for it. Over time, as thousands of these electrons hit the screen, they don't just form two clumps directly behind the slits. No, they build up a classic wave-like interference pattern of alternating packed bands and empty spaces. These electrons are literally interfering with themselves like ripples in a pond while they are in transit. Absolutely wild. The rules of the quantum realm, Schrödinger, and probability. Okay, so now that we know matter actually behaves as a wave, we have a major problem. We basically have to toss the old Newtonian rulebook straight out the window. You can't use classical mechanics for a particle that is smeared out like a wave. We're entering a highly abstract realm governed entirely by probability. Because of this wave nature, we can no longer track an electron's exact classical path through space. We can't confidently say it's exactly here and it's moving exactly there. Instead, we rely on Schrödinger's equation, advanced by Erwin Schrödinger in 1926. This beast of a formula doesn't give us a definitive trajectory. Instead, solving it gives us the space and time-dependent matter-wave function, represented by the Greek letter psi. But what exactly is a wave function? Honestly, on its own, it's just a complex mathematical quantity. But if we square its absolute value, we get something incredibly profound: the probability density. That means we don't know exactly where the electron is. We only know the probability of where it might materialize if we insert a detector to look for it. Until we actually look, the electron exists as this hazy wave of potential outcomes. When we measure it, the universe essentially rolls the dice based on that probability map to pick the particle's precise location. Heisenberg and quantum weirdness. And, it gets even weirder when we try to actually pin down these probability waves. You might be thinking, hey, let's just build a super precise microscope so we don't have to rely on probability anymore. Well, Werner Heisenberg realized there's a hard limit built right into the fabric of reality. The very act of detection physically alters the particle. Think about it. To see an electron, you have to bounce at least one photon off of it. But, as we learned from Compton scattering, that photon transfers momentum to the electron, completely changing its path. So decreasing the uncertainty in its position necessarily increases the uncertainty in its momentum. You can never perfectly know both at the exact same time. The tighter you pin down where it is, the less you know about where it's going. And because particles are probability waves, they pull off feats that seem like magic. Imagine rolling a ball up a hill. Classically, if it doesn't have enough kinetic energy, it rolls back down. If it has enough, it goes over. Simple. But in the quantum world, an electron wave hitting an invisible energy step has a measurable probability of reflecting back, even if it has plenty of energy to pass right over. Even crazier, quantum tunneling. When a matter wave hits a thin, supposedly impenetrable solid energy barrier, a tiny bit of that probability wave can literally leak through to the other side. An electron can just tunnel straight through a solid potential barrier. And fun fact, that exact phenomenon is what makes the flash memory inside your computer work. We've covered a lot of ground here. We've gone from glowing packets of photons to matter waves walking straight through solid walls. We've learned that light acts like particles, particles act like waves, and we can really only ever calculate the probability of where anything truly is. Which leaves us with one final totally mind-expanding question to chew on today. If the mere act of measuring fundamentally alters a particle, forcing it to choose a location, what exactly is reality when no one is looking? Keep that in mind next time you turn off the lights. Until next time, keep questioning everything.